Congratulations. Our next speaker will be the Chizhevsky lecture, and it's Theodosios Chizhevsky, and he will be discussing unlocking the potential of historical solar archives for Irradiance reconstructions.
Hello, everyone. So, I'm very honored to be here. I gave my very first talk in an international conference here in Coimbra in 2015. So it's really an honor for me being here 9 years later to talk to you about what we've done in this meantime, and especially for this occasion, getting this prestigious award. So, I'm going to talk to you about our work on analyzing historical data to understand irradiance variations in the past. Let me start very briefly with the motivation behind this. That is because, as we know, the sun is a very important factor which influences Earth's climate. And in fact, it provides almost the entire energy that the Earth system receives. And that is predominantly through radiation, so what we call solar radiance when we measure it outside of the Earth's atmosphere and normalized to the mean Sun-Earth distance. And this is modulated by the solar surface magnetic field. That is that, I guess you cannot see this laser. Okay. That means that the passage of sunspots across the disk, as you can see in this image, lead to a depression in TSI when sunspots reach the disk center, while when faculae cross the disk, we have the exact opposite effect. That means that with faculae, TSI increases. So the variations in irradiance are basically a competing effect of these two factors. We have measurements of TSI for the last about 4 decades. You can see some of the available measurements in this figure here. But they are mostly from different and relatively short-lived missions. And as you can see, the measurements disagree with each other, so there is an issue of how to combine them together. And this is quite challenging. And this is why it has led to a number of different composites of TSI measurements. You see some of those here. Some of those have been discontinued. I saw them just for completeness. And you see that they have a different evolution of TSI over the last 4 decades. And the other important issue is that we need even longer data sets of irradiance if we are going to understand how the sun affects climate. One option would be, of course, to use proxy solar data and extrapolate this further back in time, but that would increase, basically, take this uncertainty and increase it further back in time. And this is the picture that we have at the moment. This is some of the more recent reconstructions and some older ones of TSI that cover the last about 4 centuries. And you see they show significant disagreement. We have about an order of magnitude difference in the secular trend over the last 4 centuries. And unfortunately, this is largely because of the scarcity of data that describe faculae. As I said before, we have data for sunspots, but without faculae, we have a huge uncertainty on recovering irradiance variations. So how can we fix this? How can we make things better and get a more accurate estimate of the secular variation in irradiance over the last centuries? I'll show you a number of things that we have done. This is not exclusive. People can do more things, but we focused on using calcium key observations, which I will talk to you in a second, because they can give information about faculae for about a century. And in this way, we can improve the reconstruction over the last century, but then also improving the information we have about sunspots. We can then even get better reconstruction over the last centuries, and also understanding issues with different models. I will start with calcium key observations first. So these are full disk observations of the sun, the calcium key line. So you see some examples here. And the first observation started all the way back in 1892. And since over that period there were no CCD cameras, they were all stored in photographic plates. And we have such data up to 2007. And that introduced the first issue when one has to analyze this data, because photographic plates are not linear detectors. That means the response of the plates to the radiation is not linear and actually follows this sigmoid shape, as you can see in this figure. And if one wants to use different data and consider them in a consistent way and get meaningful results out of them, they need to account for this as accurately as possible. But unfortunately, the data did not have a way to do this straightforwardly, at least. Luckily for us, over the last about couple of decades, there have been a lot of efforts to collect and digitize the different data. I need to stress that there are quite a lot of them still missing, and it's very important to keep finding this data. And this has led to a number of different studies, mostly extracting information about the evolution of faculae or even reconstructing TSI. I show you some examples here. But unfortunately, it seems like the improvement that I was promising that calcium K would give does not arise from this image, judging from the big disagreement that different data show. And what is the cause for that? And we thought that there are a number of issues with these studies that starts with none of them actually accounted for the nonlinear response of the plates. The accuracy of the processing to remove for the different artifacts, which you can see some on the video on the lower right side, even though this is a relatively good case, and you have way worse observations than this one, but even for these ones, the different methodologies did not explain how accurately they can recover that. And then they used mostly single archives, which meant that differences between the archives were not considered. So we thought we can do better on that. And I'm going to very, very briefly mention what we've done. I'm not going to the boring technical details, but we developed an automatic process that basically managed to identify the different artifacts that affect the images, for instance, the one you see here, but then also extract what is the center-to-limb variation of the quiet sun, which we then use in a novel approach to perform the photometric calibration of the images, and then get clean images from which we can use straightforwardly and get meaningful results out of them. But we also took a lot of time to make sure that this method is robust. It works consistently and accurately. So we used a lot of synthetic data to evaluate its accuracy, so we can be confident it's accurate enough, but also can show that it works quite significantly better than other methods from the literature that have been used in the past, as you can see in this example. But also, because it was done in an automatic way, and it's quite robust, can be also used consistently for data that are quite diverse, even different lines, that includes H alpha and in the continuum as well. So we took the time to collect as much data as we could. So you see some of the examples, some of the archives that are out there. Coimbra is actually one of those. And these are about 500,000 images that we could analyze and get really meaningful results out. I will just very, very quickly, so we could get evolution of plus areas, so have a composite series out of all of those covering 1892 to present, butterfly diagram of plus areas, but also filament areas from H alpha data. But for the purpose of reconstructing right now, we need the magnetic field. And that is the most important thing for us from the calcium K data. And that is because there is an excellent correspondence between the regions that appear bright in calcium K observations and regions that have strong magnetic field in magnetograms. So by using a large sample of contemporary observations of calcium K from Rome Observatory and HMI magnetograms, we could establish a tight relation between magnetic field strength and calcium K brightness. And then we could use this to reconstruct magnetograms, and provided the data have been processed in a consistent way, we can apply this to recover magnetograms also from the historical archives. As you see some examples from Kodaikanal data more than 100 years ago. And having these magnetograms, then we can use this data to recover irradiance variations with a physics-based model like the satire, which I will show you now. So these models basically get the irradiance variations by splitting the disk into different features, sunspot, faculae, and quiet sun. And for each of those, getting intensity spectra from radiative transfer codes from the corresponding model atmospheres. The observations are used to basically track where these features are over the disk, and accordingly use the intensity spectra that were computed. So using the magnetograms we have recovered from the calcium K data, we can recover TSI irradiance from this model, and I show you an example with observations from Rome Observatory. And as you can see, compared to the measurements which are shown in black, we get an excellent agreement. But we also get very accurately the daily variations, so we can get an excellent reconstruction with this data. But we also tried it with photographic data, and we have excellent results with those too. As you can see here, for the case of using data from Medallist Observatory in Paris. But here there is more work that is needed, because with the historical data, one needs to be careful about different changes in the instrument, different inconsistencies over the years that might have affected the data. So this is the part that requires a bit more work to have the reconstruction over the full century. However, even up to now, we can get meaningful results about range variations, about the long-term trends over the period that we do have measurements. And that is just very quickly to recap that the measurements cannot give information about the long-term trend, while regression models basically inherit this uncertainty and also are cannot do any better. But we can do that with physics-based models. For those, on the other hand, we have the other issue that they're very short term series of magnetograms, which don't have a significant overlap, so there is also uncertainty with them. But using the different calcium K data, which are completely independent with each other, and getting basically the same results for all of those for different activity minima, then we can be confident that we have recovered quite accurately what is the trend between minima, activity minima over the last few decades. And with this, I also need to stress that since we have a few overlapping data over the 85-95 period, we can say much more confidently that the hypothesized increase, what is called the acrim gap, is really not seen in this data. So it's really disfavored. So I will move very quickly to the second part, that is what we can do with sunspot data to improve our understanding of irradiance variations. And very quickly to say that we have a lot of different observations of sunspots, and they differ significantly in quality. We have from CCD observations very recently some photographs, drawings of different quality, but a lot of the data are in either tables or just comments that the observers left. And based on that, we have extracted the number of groups, mostly, back to 1600s. You see in this plot in blue, basically the number of records per decade. And you can see that we have quite a lot of data over the last couple of centuries, but the data decreased significantly before that. So it's a very big need to recover more data and have and fill the different gaps we have there. So the first part is that one can improve this by getting more data. I will mention very, very briefly two cases that I was involved. That was by recovering data by Angelo Secchi in Rome, where we could recover the actual notebooks and give data for a full cycle that were previously completely lost. And this also led to a reanalysis of the Carrington event, but also the February 1872 event. Or cases that we could identify that based on the original sources, the database has incorrectly entered the number of spots, mixing sunspots with groups. So we could reconcile that and get a better estimate of what the sunspot number should have been in the early 1700s. And this is a continuing process, and here I want to take a very, very brief moment to advertise. We have a citizen science project basically asking for volunteers to help us extract information from this data, because there are too many and it's physically impossible for us to count all of them. So we're giving them small subsets of the images, and we're asking them to just tell us how many sunspots they see. We are very glad at the moment it has received quite a lot of attention, and we hope we can show results from that soon. But then we come again to exactly the same issue as I mentioned about irradiance, because we have a lot of different observers that gave information about sunspots, but they did it in a different way. They're relatively short term as well, but they use different telescopes, they have different acuities. And as you can see from these figures, these observations from the same day, but the spots that one observer sees were very different to the other. So it's again the same issue. We need to cross-calibrate the data to have a consistent time series. And that was typically done in the past by linearly scaling the data. And you can see some of the reconstructions here. But we thought this can be improved. We used a number of synthetic observations to study how this relationship changes for different levels of activity, and we could show that in general the relationship is not linear. So the question is, how can we do better with that and do the calibration in a way that accounts for this? And this is basically the scatter plot between two observers, and since the values are discrete, you see that you have a lot of overlapping values, so you don't really get much information. The red line is what was typically used in the past. What we did was basically, so here you see in numbers how many data points are basically covered with each data point that you saw in the previous slide. And we normalized each one of those basically by the total number of days, and we get this matrix with probability distribution functions that you can see. And we can use this in a very straightforward way to just directly calibrate the data from one observer to the other. That is by getting days, for instance, that observer number 2 gave the sunspot number 5, and replacing it with a distribution function we see in this curve. And that is very important because not only we calibrate the data, but we automatically have an error estimate. So we know how accurately the cross-calibration is, something that was lacking in the data in the past. And we use that to all observers we have back to the 1700s. You can see compared to the previous group number, which our update of the series shows that the activity level before 1900s was a little bit higher than what the Hoyt and Sutton ones was showing, but also that we get a better agreement with the reconstruction based on the carbon-14 data. And here I need to say that this methodology has also been used to recover the sunspot numbers, the international sunspot number series, for an interim reconstruction. It's called version 2.3, which is hopefully going to lead to the version number 3 in a few years from now. And combining the reconstruction of Irradiance that I showed you before with satire and this group number series, we could also get a reconstruction of Irradiance for the last 300 years, which is now one of the 2 solar forcing datasets used by CIMID, and it's going to be used for the next IPCC report. And I think I'm running late, so I'm going to be very quick with the very last point. I was just going to mention that there is, one can also improve on this discrepancy by understanding the issue of the different series. And there is one particular that has received a lot of attention over the last decades, the Hoyt 93, as you can see here. That's a series that has a large amount of variations and has some peculiar features that no other series has, and that means that it has a better agreement with temperature on Earth, and that has led for the series to have quite a lot of attention. The problem with this series is that although it was published in 93, the authors did not actually describe the methodology in a good way, so that it was not clear what they did. So we took the effort to try to understand this, so basically reverse engineering this method by the small bits and pieces that they gave in the paper and the different figures they had. And that led to the realization that there were quite a few problems in the way they analyzed the data. I will be very quick to say that they arbitrarily shifted in time some of the series. They added data that don't exist, which actually ended up contradicting the actual ones, but they also incorrectly connected data that was highly anti-correlated. So if one were to correct just for these 3, not all the issues, that is enough to remove the sharp increase that this series was showing over the last decade. But the more important part is that this large amount of variation that this series was showing, it was not something that was a result of the model. It was something that they imposed on it arbitrarily. So by using the methodology as we understand it and using more recent data to update it, we could contrast it to actual TSI measurements. And we can see that the scaling of the variation that they used is quite inconsistent with direct TSI measurements. While to make it kind of consistent, one has to use at least 5 times lower magnitude variations than what they used. And just to finish to say that this series was given to have a very good correspondence to temperature on Earth. So this is the original one as they had it in '93, and they were getting a correlation coefficient of 0.7. But if one were to correct for the artifacts that I told you, that drops dramatically to 0.16, and now the series is actually in a significantly better agreement with other current series of Irradiance. And with this, I will leave you with a summary slide, and thank you for your attention, and sorry for being late.